Hi everyone, I'm Wijland. I'm going to talk about an improved greedy approximation for metric k-means. This is based on my joint work with my advisor Moses and other collaborators Vincent, Fabrizio, Jovan, and Ernest. In this talk, we'll consider the metric k-means problem. Well, we are given a metric space and two settings in the space representing the clients and the candidate centers. The objective is then to find k-centers from the candidates that minimize the sum of square distances between each client and its closest chosen center. The set of clients sharing the same closest center can be viewed as a cluster. This is a generalization of the well-studied Euclidean k-means problem, where the space is Euclidean. In the continuous case, the center can be chosen anywhere, while in the discrete case, the candidate centers are given by the input. Moreover, in the continuous case, if a set C forms a cluster, the optimal center should be the mean of points in C. Because there is a polynomial time reduction from the continuous case to the discrete case, only losing a factor of 1 plus epsilon, we usually consider the discrete case when designing approximation algorithms. This Euclidean setting is also well known because of a simple local search algorithm, the noise algorithm. In the algorithm, we start with k arbitrary centers, while traditionally the k centers are uniformly sampled in the Euclidean space. Then we repeat the local search until convergence. In each step, we assign each client to its nearest center, and then the k centers are computed by the mean of all clients assigned to it. Because of the simplicity, the algorithm is broadly used in practical settings. As a theorist, we may care more about the theoretical guarantees of this simple algorithm. On the time aspect, it can only converge in exponential time in the worst case. For smooth analysis, it can converge in polynomial time. On the approximation guarantee aspect, it does not have any approximation guarantee without any warm start. If we use the k-means plus warm start, then the approximation ratio is in the order of log k, which is not a constant. So it would be more interesting to ask if there exists a constant factor approximation for k-means problem. Other than the lowest algorithm, local search with more sophisticated strategies can be a 9 plus epsilon approximation for the Euclidean case and a 16 approximation for the metric case. Later, a breakthrough result improves the ratio using variance of the Jane-Vazirati algorithm, which was first introduced for the k-median problem. The current best ratios for k-means are now 5.913 for the Euclidean case and 9 plus epsilon for the metric case. On the other hand, there have been many results on the hardness of k-means. However, the gap between upper bound and lower bounds are still very large. In this work, we substantially improve the gap between the upper bound and lower bounds by presenting a 3 plus 2 times square root of 2 plus epsilon, which is about 5.83 approximation for metric k-means problem. This improves both upon the 9 plus epsilon approximation for the metric case and the 5.92 approximation for the Euclidean case. A closely related problem is the k-median problem, where we want to minimize the total distance instead of the total squared distance. Similarly, constant factor approximations are known, and the current best ratio is a 2 plus epsilon approximation for both the metric and the Euclidean case. Next, I will talk about the techniques used in this paper. To deal with the constraint that there are exactly k centers, we consider Lagrange multiplier preserving approximations. In details, we consider the closely related facility location problem. Instead of restricting the number of centers, the problem considers an opening cost for each center, or say for each facility. The objective is then to minimize the total opening cost plus the connection cost. For comparison, the k-means objective only has the connection cost part. To apply for the k-means problem, the objective is to find some LMP approximation whose opening cost plus connection cost is at most the opening cost plus a gamma times the connection cost of any optimal k-means solution. And this is different from approximation ratios for the facility location problem because we cannot have a ratio between the opening costs. Technically, k-means and k-median share a lot of algorithmic ideas. Jean-Mazzarani proposed a simple 3LMP approximation for k-median, and it is then generalized to a k-means with a 9LMP approximation. After J.V.'s work, Jim Mahadian and Saberi introduced another simple 2LMP approximation for k-median, and it is recently proved by a group of researchers that it leads to a 2 plus epsilon approximation for the k-median problem. However, folklore counterexamples exist for simple adaptations of this GMS algorithm on the k-means problem. In our work, our main technical contribution is a GMS-like 5.83 LMP approximation. Using this LMP approximation, the framework of the 5.83 approximation for the k-means problem is combining two algorithms. The first one is a bicriterial approximation, where we start with a gamma LMP approximation and then use the framework of CGLSS for a gamma plus epsilon approximation, which opens about log n over epsilon squared additional centers. The second one is a 5 plus epsilon approximation for stable instances. Well, the stability is defined by the optimal cost with opening k-1 centers is beta times larger than that with opening k centers. Our algorithm is in polynomial time once beta is as large as 1 over log n. This part also follows the framework of the previous work. Putting these two algorithms together, we can run algorithm 1 with k minus delta, where delta is about log n over epsilon square, and then run algorithm 2 on every number between k minus delta and delta. If algorithm 1 does not provide a gamma plus epsilon approximation, then at least one run of algorithm 2 gives us a 5 plus epsilon approximation. So the best solution we find from these executions is a gamma plus epsilon approximation for k-means. Next, we will focus on our main technical contribution, the gamma LMP approximation using a variant of the GMS algorithm. As in the original paper introducing the GMS algorithm, we'll continue using dual fitting for the analysis. In the dual program of the problem, we have a dual variable alpha j for each client j. And the only constraint is that the total dual contributions of all clients to any facility cannot exist the opening cost f, while the dual contribution of client j to facility I is alpha j minus the square distance between I and j. Based on this primal dual relaxation of the facility location problem, the dual fitting process is to maintain some dual variable satisfying reverse duality and the approximate dual feasibility. The reverse duality asks the dual objective to upper bound the total cost of the LMP algorithm. The approximate dual feasibility asks the dual variables alpha divided by some constant gamma is a feasible dual solution. With these two properties, we can show that the algorithm is a gamma LMP approximation. Then, the original GMS algorithm for the K-median problem is as follows. We initialize the variables to be 0 and make every client active. Then we continuously increase the dual variables for active clients with the time until one of the following conditions holds. The first one is that for some active client J, its alpha value alpha J is greater than its connection cost to the closest open facility. The second condition is that some unopened facility is openable. Well, the openability is defined by that the total bids of the clients is greater than or equal to some f hat. Well, the bid of active clients equals to its dual contribution to the facility, while the bid of inactive clients equal to the total improvement of switching to this new facility. Intuitively, the active clients will use their dual variables to pay for the opening cost of the facility and the connection cost, while the inactive clients will use their old connection cost to pay for the opening cost and the connection cost. After that, all clients whose alpha value is enough to pay for the connection cost will become inactive. So here, alpha j is the time that j becomes inactive. For example, at time 3, bids of clients EFG are available to pay for facility 3. So facility 3 is open. Then at time 4, bids of clients ACD are available to pay for facility 1. At time 5, the alpha value of client B reaches D1B, so B becomes inactive. At time 8, facility 2 becomes openable because clients BDH have bids 2, 1, 3 to this facility respectively. Then, a straightforward observation about this algorithm is that it ensures the reverse duality. To establish approximate dual feasibility, it is sufficient to show that the sum of alpha values in D star is at most f hat plus twice the sum of dji in D star. Here, D star is the set of clients whose alpha value is greater than twice of dji. Then the first constraint we can obtain is that at time alpha j minus any sufficiently small epsilon, client j is active. Therefore, we can write that alpha j is less than or equal to rj prime j plus dji plus dj prime I by the triangle inequality, and where rj prime j equals to dj prime s if j prime is inactive at this time, alpha j minus epsilon, or it equals to alpha j prime otherwise. The second constraint is obtained while the fact that at time alpha j minus any sufficiently small epsilon, facility I is not open. So by the definition of openability, we can show some upper bound for the sum of rj prime j. Then we can apply the lower bound of rj prime j in the first constraint to the second constraint without any scaling. So we can get some desired upper bound for each alpha j and what we want to show. Next, we consider the simple adaptation of the GMS algorithm to k-means, where we simply change all connection cost from distances to square distances. However, this will impose a very serious issue in the analysis, where the key triangle inequality bounding alpha j by dj prime s will have some coefficient which is strictly greater than 1 before both d squared j prime s and the remaining terms. To use this weak triangle inequality, we need to scale it by a factor of 1 over gamma. As a result, it can cause the approximate due feasibility to collapse because we will have a non-trivial 1 plus delta coefficient before f hat on the right-hand side. Moreover, in our paper, we present a concrete counterexample for this simple adaptation. In this counterexample, there are two clients that don't have any bounded LMP guarantee. Though we will not present the details of this counterexample here, we want to remark one important observation about this counterexample, which is that GMS fails on this counterexample just because there is a client whose connection cost is strictly less than, but is very close to its alpha value at some point of the algorithm. If no such client exists, in other similar examples, we can show that GMS has a constant factor LMP approximation guarantee. Therefore, this inspires us to design a new variant for the GMS algorithm on k-means. Recall previously in the simple adaptation, we define a client to be inactive if the alpha value is no less than its connection cost. Here, moreover, we distinguish two types for the inactive clients. The first type is directly connected ones, which means that the client contributes some of its alpha values to the opening cost of some facility. That is, alpha j is strictly greater than its connection cost d squared js. The second type is indirectly connected clients, which means that the client only pays for its own connection cost. Then we can rewrite the openability condition where for directly connected clients, the bit equals to the improvement of switching to connecting to this new facility. For indirectly connected or active clients, the bit equals to its due contribution to the facility. With this distinguishment, the previous issue is all about directly connected clients, J with d squared js close to alpha j. So we can have a different definition for directly connected clients to resolve the issue. Well, we want alpha j to be greater than a gamma times the connection cost for directly connected clients. We will then redefine the bits in the openability condition. Well, for directly connected clients, the bit equals to gamma times the improvement of switching to connecting to this new facility. For indirectly connected or active clients, the bit is then equals to the alpha value of it minus gamma times the connection cost. With this new definition of bits, we can apply the weak triangle inequality into the openability condition without any scaling. Finally, by dealing with all different possibilities about IC and DC, we can prove the approximate due feasibility by a factor of gamma plus 2 gamma over gamma minus 1, which can be optimized to about 5.83. And this is a key idea how we get the improved ratio for the k-means problem. For conclusion, the main takeaway message for this talk is that the GMS algorithm for k-median can be adapted to a 5.83 approximation for metric k-means, which improves the previous ratios of metric and Euclidean k-means problem. For future work, the most straightforward direction is to further improve the ratio of k-means. In our work in progress, we have a 4 plus epsilon approximation for Euclidean k-means by introducing some new ingredients to this adaptation. Because it is very close to the currently best 3.94 lower bound of metric k-means, it would also be interesting to ask, can we have a separation between metric k-means and Euclidean k-means? Finally, it would be interesting to ask if our new idea can be applicable to other k-clustering settings, such as k-median and k-mean sum. That's all, thank you.